Today we're going to look at factors that affect the rate of a reaction, and this study of rates of reaction, how fast a reaction takes place, is called the study of kinetics. Kinetics is the branch of chemistry that deals with how fast reactions occur or how slowly reactions occur. So kinetics is our topic for today. And if we think about factors that affect the rate of a reaction, how fast a reaction will go, we can think about things that would speed up a reaction or things that would slow down a reaction. And when we talk about a reaction, we're talking about two different substances. Let's talk about substance A and substance B. And these two substances, when added together, will react. They'll either form a new compound, or they could break apart and form separate elements. They could make multiple compounds. But the idea is that they have to collide with one another in order to react. And this idea that two substances have to collide with one another in order to react is called collision theory, which makes sense. But collision theory says that in order for two substances to react, they have to first collide with one another, and when they collide, I can't spell. When they collide, they have to collide with enough kinetic energy, and which means they have to hit with sufficient energy to actually react with one another. So this reactant has to hit this reactant with enough energy to actually react. And then the other thing is that they have to hit with the correct orientation. And orientation means arrangement. In other words, the correct side of each molecule has to hit with one another. For instance, if you think about water molecules are bent. And so one side of the molecule is very different than the other side of the water molecule. And so if it's going to react with something, the correct side has to hit the other molecule correctly. And that's what I mean by orientation. So each of these things has to be true. They have to collide with one another with the correct kinetic energy and the correct orientation in order for the reaction to take place. So if we're going to talk about kinetics, rates of reactions, we always need to keep that in mind, that molecules are running into each other with kinetic energy, and they have to have the right orientation. So collision theory is a major part of this. So what factors would affect the motion of a molecule? Well, if you think about it, temperature is a key factor that talks about motion of molecules, because temperature is the measure of their motion, their kinetic energy. And so if you have high temperatures, then that's going to make the molecules move faster with more kinetic energy, and that means that the reaction will go faster. Okay, so high temperatures cause a faster reaction because the molecules are going to move more quickly, and the molecules are going to collide with more energy, and there's going to be more collisions, and more collisions means faster reaction. At low temperatures, you're going to have a slower reaction because the molecules have slowed down. There's not as many collisions, and so therefore the reaction will go slower. Another factor that's going to affect collisions is surface area. And what I mean by surface area is how much of the surface of a reactant is exposed in the reaction. How much of a reactant is exposed and capable of reacting. And to think about surface area, let's think of a log. Okay, if I have a log and I put it in my fireplace and it burns, only the exterior of the log can burn. So the top of the log, the sides of the log, but the interior is not exposed. The surface area of the interior is not exposed, and so it can't burn. If I wanted to burn the inside of the log, I'd have to expose it to air so that the reactant oxygen could get to it. So if I cut this log in half and have two pieces of log, so one piece, two piece, still the same log, but now we have this area that can react, the top. We have all the sides that can react, and now we have this interior surface that can react. We have more surface area. If we cut it in half again, and cut it in half again, and cut it in half again, and cut it in half again, we'll continue to have more and more and more surface area. And if we make it into sawdust, the exact same amount of log, but make it into sawdust, every single particle now has a huge amount of surface area that can react with the oxygen around it. Still the same amount of wood, but now more surface area, so the reaction can proceed faster. So more surface area, like a powder, can react faster than less surface area, like a big solid piece of material. Okay, so more surface area means that you can have a faster reaction, and less surface area means you'll have a slower reaction. Okay? A third factor that can affect the rate of reaction is concentration of the reactant. Now, if you recall, concentration means how much of your reactant is dissolved in a solution. So let's say that you have two beakers, and our reactant is hydrochloric acid, HCl. And in one beaker, we have this much water, and in another beaker, we have the exact same amount of water. And in the first beaker, we put a whole bunch of HCl. Okay, each dot is going to represent a certain amount of HCl, and we have a whole lot of HCl in this beaker. And in another beaker, exact same volume, we have very little of the reactant. Okay, so here in the left beaker, we have a very high concentration. In other words, there's a lot of reactant per volume of solution. In this beaker, we have a low concentration. There's very little reactant per volume of solution. So which one do you think is going to react faster? Well, the one that's going to have more collisions with the reactant, our high concentration. So our high concentration of reactant is going to go faster, and our low concentration of reactant is going to go slower, because the high concentration will have more collisions and our low concentration will have fewer collisions. The last factor I want to look at that affects the rate of reaction is how long has the reaction taken place. In other words, how much time has elapsed for your chemical reaction. And so let's go back to our concentration, and let's say that we have the HCl reacting with a piece of metal. HCl reacts with metal to form hydrogen gas and a salt. And in this chemical reaction, when I put the metal in, it's going to start reacting with our HCl molecules. And over time, the HCl molecules are going to start reacting, and they will be gone. They've reacted and become something else, so they can't react anymore. So as there becomes less and less reactant in our solution, the reaction is going to slow down. And eventually, if all of the reactant gets used up, the reaction will stop. If we want to get the reaction going again, we would need to add more reactant. So more reactant, put the metal back in, and the reaction will start going again. But again, as the reaction takes place, the reaction is going to slow down because our reactant's getting used up. And so in this example, as the reaction takes place, more time goes by, the reaction's going to slow down. So as more time goes by, the reaction's going to slow down because our reactant's getting used up. And so those are the four factors that we're looking at today: temperature, concentration, surface area, and elapsed time, and how they affect the rate of reaction. So if we look at this graphically of what's going on in a chemical reaction, we can use what's called an energy diagram of this reaction, where we have energy on the y-axis, and we have reaction progress on the x-axis. And in any reaction, the reactants will have a certain amount of energy to begin with. Okay, so this up here is our reactant, and they have a certain amount of energy. Our products are also going to have a certain amount of energy, and in an exothermic reaction, they will have less energy. And we've talked about this in the past. So reactants are going to start with certain amount of energy. Our products, sorry about that. Our products will have a certain amount of energy. And between the reactants and products, there is what's called the activation energy, the amount of energy required to get the reaction going. And that's this amount of energy right here. We have to raise the energy of the reactants, which is basically energy used to break the reactants apart so they can then go bond with the other reactants and form the products. And so this is called the activation energy. Activation energy. And that's what controls the rate of the reaction. How much energy is required to get the reaction going. The higher the activation energy, the slower the reaction will go, because it takes more energy to get it going. So if we have a high activation energy, the reaction will go slower. If we have a low activation energy, the reaction will go faster. So how could we lower this activation energy? In other words, how could we provide a alternate pathway for the reactants to become the products? And the answer is a catalyst. A catalyst is a substance that speeds a reaction up. It provides a different way for the reactants to become products. And when a catalyst is used, the activation energy actually will decrease. And so I'm going to represent that with a dotted line here, where the catalyst makes the activation energy lower, and therefore the reaction goes faster. So a catalyst is a substance that causes a reaction to go faster, but doesn't get used up in the reaction. In other words, at the end of the reaction, we'll still have our catalyst left over. We'll also have our products. And our products came from the reactants. The catalyst is what we added and gets left over. It just sped the reaction up. There's also another substance that's called an inhibitor, which you normally don't hear of. But an inhibitor is a substance that slows a reaction down. And so if you want to slow a reaction down, you add an inhibitor, and that causes the activation energy to increase. And so with an inhibitor, the activation energy will increase. So a catalyst lowers the activation energy, an inhibitor raises the activation energy, and that changes the rate of reaction. So that's our introduction to kinetics today. I hope you learned a lot, and look forward to talking to you soon.